Hello, welcome to SDC 2020. This is Peter Scott and Rajesh Gupta talking on OS level encryption and access control. I am a principal software engineer at Thales, and Rajesh, my colleague, senior development manager, and he will open up the talk.
Yeah, thank you, Peter. Thanks, everybody. Welcome to SDC 2020. So just want to give you a background on us. So Thales, in the Cipher Cloud, Cipher production and licensing division, we protect the data. And this is what we want to talk about today, basically how this data is getting more valuable for all these companies and how these threats to these businesses are coming up and how we can protect that data. So data is everywhere nowadays. And the research has shown again and again that volume and value of data is increasing exponentially in this data age. So I like the way Splunk put it in one of their blog. They said this quarter century of digital transformation has gotten us into this. Now, companies are not just after your financial records, not just your medical record, they are collecting data everywhere. They are collecting your driving history. They are collecting your shopping habits. They are collecting all kinds of data from everywhere. And this data is valuable. And this brings a lot of threats to businesses. I mean, there are pretty much every day we see data breaches are happening at the companies. Ransomware attacks are happening. Privileges, credentials are stolen, and data breaches are happening. So if you look at basically 81% of the companies, they feel that data is very valuable to them for the overall success of the company. And 47% of feels that they are far behind on protecting this data. And in fact, 26% of the companies, they have admitted of being breached in past year. So that's a pretty big number, and this data is being very valuable. Next slide. When we are talking about this data, this is I like these quotes from Bruce and Kevin. He put it pretty nicely. Not all encryptions are same. There are two kinds of encryption: one which will prevent your system from reading your diary, and other is which will prevent your garments. So encryption solutions are available everywhere. You can have disk level encryption, you can have encryption at storage, but that's just a very basic, just a tick mark on your data. Does it really protect you? Maybe not. And there, you have your laptop, you're carrying some critical data, some critical information in your laptop. You go in a cafe, you open your laptop. I mean, you are susceptible to all these attacks. You walk out of your laptop and you are logged in, and all this information is available. And similarly, basically, that's one of the weak link. And another weak link is basically in the corporations, the people who are managing your systems, who are the administrator, who has the privileges, who has the administrative level privileges. They can look at their data. You have to protect that data. And this is the critical information this is the critical information and valuable information which you need to protect. So what are the top security challenges in the storage industries? So the biggest challenge is encryption. It negates compression and deduplication. So we all know when the encryption is enabled, compression and deduplication algorithms, they don't work really well, and they are not efficient. We don't have improper access controls. How do we protect this data from administrators, from the people who are managing this data? Are your backups secure? How these backups are taken? All those snapshots and everything. And there is no proper privileged access control in the storage industry. And there are a lot of ciphertext attack. We know known plain text attack. We know chosen plain text attack, once you know the ciphertext and the plain text, with the brute force mechanism, they can find your keys. To protect from all those attacks, you need to rotate your keys periodically. You need to encrypt data. Rotation doesn't mean you can just simply rotate the master key. You have to rotate your data. You have to change your data, ciphertext data. And while all these corporations are basically rotating their data, changing their keys, protecting all these huge infrastructures, managing the large number of encryption key is also a big pain in the storage industries. Insufficient separation of duty. So you have security admins, you have system admins. There are who is defining the security policies. Security team is defining the security policies while system admins are implementing those security policies. How these separation of duty will work together, that's a really big challenge. And some of these policies, they don't want to share with the system admins. They don't want them to know who has access to data, who doesn't have access to the data. So they are maintaining all the credentials, they are managing your Active Directories, they are maintaining your backups and everything. So that separation of duty is very critical as well. And one of the biggest challenges is the secure replication. So if you have two nodes on the storage, how do you replicate data from one node to another node securely? The data in transit is also can also come under attack. So these are some of the top security challenges which we will try to address. So to protect your data from all these attacks and all these the exposures and everything, you need layers of protections. Layers of protection doesn't mean just encryption. You need to have encryption, access control policy. You need to have you need to control your data from privileged users. You need to have proper auditing, proper logging, proper access controls. And also basically you need to have a centralized key manager and data access control policies. So when we talk about the access control at OS level, when we talk about the encryption at OS level, basically when we are talking about protecting the data at the OS level, we can provide layers of encryption. And we will go into details, and Peter will walk you through all those details, how we can provide it. So just simply, encryption is not enough. Encryption can be broken with the access control, with auditing, with centralized key management, with the rotation of keys. All these put together will provide a strong encryption or strong data protection at the OS level. So from the access control perspective, you can have a very fine-grained access control at the OS level. So you can identify the users. You can identify the process context. You can identify when they are trying to access the data, what kind of operation they are trying to perform on the data. All that access control can be done at the OS level, and it's all transparent to the applications. Customers or user doesn't have to change their applications. This layer is totally transparent to them. And at the OS level, we can identify the user, we can implement those policies, and what time, and you can do a very granular level of what kind of operation they can perform. So let's say authorized user, they can read and write the data, but they cannot probably delete the data. And when it comes to the root users or administrators, they can take the backups, they can maintain the data, they can do the normal administrative operations on the data or on the servers, but they cannot read and write the data. Once they try to read and write the data, they will get the ciphertext. So at the OS level, all this becomes very transparent and very and no application needs to be changed. So when we are talking about the enhanced encryption and protection, so as I said earlier, you can enable encryption at the disk level. You can enable encryption at the OS level. It's just a check mark. So once you combine this encryption with access control, that makes it pretty strong. And also at the OS level, you can also provide per file or folder. You can define per file and folder level encryption policies. You can choose unique identifiers, unique initialization vectors, IVs per file. You can rotate your IVs on various file operations. Let's say if a user performs overwrite operations, you can choose and change the IVs. If you want to provide more protection, you can change the IVs on write as well. So this is all to provide enhanced encryption rather than just a tick mark. And another advantage of enhanced encryption and at the OS level is you can transparently rotate the keys. Rotating the keys, as I said earlier, is not just changing the master key, it's also decrypting the data with the old key and encrypting with the new key. As the data is growing, now companies have large amount of data. Transforming that data reliably without bringing your application down, the production servers down, is a critical key. So that's where basically all that transparency that can be provided at the OS level. And also another advantage what we have, what we can provide at the OS level is the encryption metadata. So every file contains metadata. So you can have 10 different files, you can use 10 different keys, you can use 10 different policies on that, and all that information can be maintained inside the metadata. And that we can provide at the OS level. So far we have talked about protecting the data at the OS level, mainly at the file system level, where various file operations are happening, and how do we combine this with the encryption policy, as well as how do we control from privileged users. Now you have a device, and smart administrator, they can write a simple application and they can try to access the device directly. They can totally bypass the file system, open the device directly. They can read the NTFS extent, and through the NTFS extent, they can simply look at the data. Even if they don't want to look at the data, they can simply destroy the data, or they can encrypt the data at the device level from sector on sector by sector basis, and held companies at ransom. And how do we protect from those kinds of attacks? So in this, you can get the process context at the storage level, at that layer. And from that process context, we can provide what kind of protection and which applications are allowed it to access these devices. So you can create a whitelist, application whitelist. You can sign those whitelists for more protections. Once you sign them, if there is any injection happening inside those applications, or those application has been changed, they will not be run on the application. And so basically you can have only trusted applications are accessing my device, performing operations on my device, as well as reading the data from my device. So as you can see, these layers of protection from top to bottom are needed to actually protect the data. So next slide, Peter. So yeah, so I just gave an overview. So now I will hand it over to Peter, my colleague, and he will take you into the design of how all this can be achieved at the OS level and at the storage level. So Peter, to you.
Thank you, Rajesh. Yeah, so I'm going to dive into, at first, just sort of a higher level look at the design. And just as a side note, we're primarily coming, this talk anyway, is primarily coming from the Windows side of the design. I'll be discussing some aspects of the Linux, but primarily for in terms of the design and implementation coming from the Windows perspective. But first off, just as a quick overview, I want to talk about just the layered aspect of drivers, file system, storage drivers within the Windows kernel. This diagram shows the sort of a very high level. Lots of modules, of course, have been removed for simplification, but it shows that a file system in the Windows kernel gets requests via the I/O manager from applications. All of the accesses are controlled through file objects that can be integrated with the cache manager, memory manager, and then everything that goes out below the file system is directed towards the storage, either local or across the network. The next slide here shows how a layered file system can be introduced into the system to be able to implement a lot of the features that Rajesh has described previously. And with a layered file system, which we'll get into more details on, allows a design to take over accesses to given files or directories on behalf of the underlying file system, though leveraging many aspects of the underlying file system, so that the layered file system can, for example, integrate with the cache and memory manager, but not have to worry about the persistence of the namespace to disk and those different aspects. So just a sort of a high level, which we'll be referring back to during the talk. So much of the access control that the layered file system provides is allowed through the ability for the layered file system to be able to extract user information as the requests are coming in. And so because of that, we can implement a lot of these the access controls, metadata management and such that Rajesh had referred to, as well as doing per file integration. So, things like integrating with the cache and memory manager to be able to expose different data views and such can be implemented through the layered file system. Yet you can choose within the layered file system what aspects you want to be able to control. As I noted, maybe there are some things that wouldn't be needed, such as persistence of the namespace out on storage and things like that, and we can just push that down into the underlying file system. But then things that may sort of fall into the gray area are access rights, whether the requester is asking for read data, write data, read attributes, and that's going to change whether it's a local file system or a network-based file system, and I'll touch more on that shortly. So then, one of the points, the sort of the top level points, are access controls. Not the access control for the credentials, but simply access control to be able to limit a user accessing specific directories or files. And so at the layered file system level, we're able to extract this user information to be able to apply different policies based on that user or possibly the user group, and what file types they can access, or what access rights, they have two different directories and files. And other, types of access control that that can be leveraged at the layered file system are, whitelisting applications. For example, a name-based policy. Name-based policies aren't ideal in terms of process names, but they give you a level of granularity in terms of control. We could also implement hash content of a given application and be able to control how those applications are loaded, if they're loaded, etc. One aspect that sort of layering on this that Windows provides is an object manager interface. So using this object manager interface, we can control how processes interact with one another. If process A can open up process B to be able to read the virtual address space of that process, or to write to it and potentially doing a remote thread exploit or something like that in process B. So we're able to control those aspects of the process interaction and how they interact with one another. Another aspect which can be leveraged in a layered file system is actually basing user access or group access to content. And so you build up this database basically, and you tag files specifically for particular types of access from users or groups of users. And as Rajesh pointed out, this is all of the policy information that you can implement, and you can have, as you can see, a wide variety of different types of policies in terms of access control. On to the next. So getting back to the encryption aspect and the data hiding aspect, one of the points of that Rajesh had brought up is the per file metadata that's associated to a given file to be able to control such thing or maintain such things as the IVs. And if a given file is getting rekeyed on while being accessed, where the left and right keys are, and that type of metadata, what we do is you can store that in a header on the given file, and with a layered file system, you are able to easily hide that header, adjust offsets, change sizes on directory enumerations, different, a lot of that is with a layered file system where you actually take over ownership of the upper level file objects, is much easier to implement than a standard file system filter driver where you're not taking over ownership, because there are aspects of the operating system for direct callbacks from cache manager and memory manager into the file system, where if you're just a standard file system filter driver, it makes it very difficult at times to be able to accurately adjust these file sizes and hide the header and different things like that. The other sort of nice little feature that you can play games with in terms of data exposure is to, when integrating with the memory manager or cache manager, you can expose different sections for a given file. So if there are different applications that have different needs in terms of their access to the clear text or ciphertext of the data, you can actually expose different sections, which will show in one section clear text data, in another section the ciphertext data. So, for example, a standard application doing memory mapped I/O or cached I/O to a file would be given clear text access in that section. If another application, for example, a backup application, is using memory mapped access, you can expose a section that exposes the ciphertext. Obviously, if you're exposing a section in ciphertext, it would be a read-only aspect because there would be almost impossible to be able to write to those ciphertext sections and without corrupting the data. So next, the next point is the sort of moving down the stack. What we've been discussing with the layered file system allows per file control and access to directories and such. There's another level of protection which is exposed, and that is at the device level, which in the Windows operating system is generally implemented through a storage class filter driver, which sits above the device, the disk device, and does encryption instead of on a byte granularity or control on a byte granularity, does it at the sector level. At this level, one of the things that you potentially lose is the ability to actually get any sort of user context that's accessing the device. There are pathways where applications can open up devices directly, and so a storage class filter can implement access control via those avenues, but in general, at that layer, everything is accessed in the system context. But the advantage here at the device level, short of course, the system and boot partitions, just for straight data partitions, is that the data is encrypted on a sector boundary. So there's you don't have to deal with the straggling bytes at the end of a given file or anything like that. Everything is full sector aligned, everything. It's not per file. The key management aspects are per device. So it's, and you can actually implement this in such a way to support if storage vendors have data compression. You can have callbacks in place, even though encryption generally negates any type of compression. You can integrate with storage vendors to be able to decrypt the data, compress, re-encrypt different avenues like that. So we'll jump a little bit deeper into the design here in terms of what it actually means for the LFS to be taking ownership, some of the details of the implementation or the design, and so forth. So on the again, this is coming from the Windows perspective. What does it mean to actually take over ownership of a given file object? So if you recall, in the diagram, with the IO manager calling into the file system, the IO manager is the component that will initialize a given file object and initially pass it down to the file system during open or create time. But that file object is predominantly uninitialized. There's a lot of pointers in it that haven't been initialized. It's, and so the file system is the one that will take over that file object, and it takes over the file object by setting up pointers within the file object that it understands. For example, there are two file system specific pointers, the FS context and FS context 2 pointers, which are taken over by the file system to be able to maintain information about that given file object. In general, the FS context is a per file pointer, so it controls or maintains information across all opens of a given file. And the FS context 2, again, in general, is a per open context. So that, for example, once a file gets opened and the file system initializes these pointers, later on, if it gets a read or a write request, that it can access these pointers and determine whether or not, how to control those I/O requests, where it's going. In particular, in a layered file system, when it takes over the upper level file objects that are coming in from the I/O manager, it will set these pointers up as well as some other pointers such as the section object pointers and things like that. And it will then independently open up a file object using one of the FLT create file variants to be able to open up an underlying file object, which it uses to communicate for that file down to the underlying file system. So it's sort of being a proxy between these two file objects, but the layered file system has fully taken over ownership of the upper layer file object. And the importance there is, I touched on it briefly, is that there are callbacks within Cache Manager and Memory Manager that are registered by the file system or the owner of the file object that the Cache Manager, Memory Manager will call directly in to pre-acquire locks on files and to be able to control the locking hierarchy and things like that. And so there, when you're just a straight file system filter driver and not taking over ownership of the file object, then there are a lot of these aspects that become very difficult to maintain. And so a layered file system actually allows you to be able to control these aspects with a finer granularity. And then the all of the caching interface is maintained at the layered file system, and only non-cached or paging I/O or things like that are actually issued down to the underlying file system. So some of the issues that need to be dealt with when you're adding a header onto a given file, I touched on briefly, are a lot of the size faking that's required, and reporting say for instance, you have a fixed 4K header at the start of a file, so you have to, if there's no data in the file, you have to report that file back to whatever component as a 0-length file, and that's directory enumerations and things like that. And with one of the advantages of using a header versus a footer is that, and you can get around it in some regards, it just complicates things with a footer. But with a header for directory enumerations, you don't have to actually open up the file to determine what the size of the file is. If it's a 4K header and it's 13 bytes, then the size reported from the underlying file system is 4K plus 13, and then so you just know to be able to subtract off that 4K from the reported size to get to the true size. Whereas if you have a footer and it's unaligned, and you have those straggling bytes, then paging I/O or actually writing to the footer can become problematic, or there are different aspects that make a footer just a little bit more complicated, although all of the issues can be overcome. But it's a header is just a more straightforward way, and the choice that we made in terms of doing this. Now, in the header is where you store the information about the initialization vector and the rekey metadata of where the rekey is going on in the file and different aspects like that. And so one of the things that that really sort of throws a wrench into all of the works are support for SIFs and NFS. one of the things that there are many aspects, which I'm just going to hit on a couple of them. One of them are for local file systems. Basically, when we open up that lower file object to be able to communicate with the underlying file system, for a local file system, we can just our access and our share that we request on that file can just be any access and full sharing. And then at the file system level, we can implement, at the layered file system level, we can implement the enforcement of the different access checks and things like that. For SIFs and NFS, because there's no direct client-to-client communication, and we're assuming that the LFS is installed on the clients, not on the server. Since there is no direct client-to-client communication, which would be one way to solve this issue, without that, we need to push off everything to the server. So we can't, whatever the caller is asking for in terms of their access and share, we have to push that directly off to the server. So in a multi-node environment, if one client opens up a file exclusively, when another client tries to open up that file, they'll get denied access. And so where the complications come in terms of this aspect is simply we have a header that we need to read. And so if the caller isn't asking for read access on the file and it's the first access, we need to figure out, how to be able to read in that header. There are some tricks you can play. You can add in execute, which will always allow you to read the header in and piggyback off of the open file object. You can have side channel file objects that are very transient to be able to open up the file if the caller isn't asking for read access, read in the header, different things like that. They all have their complications, but they're all surmountable. There isn't anything that isn't insurmountable as of yet. Another aspect are opportunistic locks. Opportunistic locks are generally provided for cache coherency between clients, so that if a client takes a read-write opportunistic lock, it knows that it can read and write the data locally in the cache and not worry about other clients accessing those files. A read-only op lock, they can read data locally, but all writes have to go all the way through to the server. So the opportunistic locks are a complication in the layered file system because only RDBSS, which is the SIFs implementation on the client, can request opportunistic locks from the server. And so luckily, Windows provides an interface. I term it sort of layered op locks, where we can actually piggyback off of the op locks that are requested by RDBSS, or RDBSS will request op locks on our behalf when we request them. And so, of course, this interface is completely undocumented, and there's lots of possibilities for deadlocks in the system, but you can get around it and be able to implement the opportunistic lock interface between clients in a safe manner. One of the other aspects that is interesting on the SIFs NFS aspect is to be able to perform rekey of file content across the network. And so, of course, in that model, you have to have some sort of central point of communication between the different clients to be able to ensure that when one client is rekeying a large file, that the other clients are using the correct key to either read or write the data that's happening on that file that's being rekeyed. And so you have to have some sort of one client or one system that does the sort of the central management of the control of the files, and it definitely gets into some complex scenarios. So just going into just some closing thoughts here. You know, as we all know, data breaches continue to escalate. As high as the people that are protecting the data can raise the bar, the people that are trying to steal the data matches it. Internal compliance to be able to protect the data internally is just becomes more and more difficult, more and more cumbersome, just because of the need to be able to protect the data from outside exploits. And of course, as we all know, whenever one of those breaches do occur, it can be devastating to the company, very time consuming and costly. And then just some sort of thinking forward, just in terms of how to be able to keep this data protection moving forward. You know, some of the things are how to better protect internal exploits, disgruntled employees, and you know, pushing data to the outside, or maybe some sort of phishing attack has introduced an internal exploit that will then be able to push data out. Moving all of the data to the cloud. How do we better control aspects of data that are, you know, that's pushed into the cloud, and other vectors that can come in and access that data, and how it all is controlled, and integration into the operating system. And on Windows, of course, you know, for the Azure access, it's very integrated into Explorer or through Web Client, which makes sort of the quote layered file system approach a little bit easier, but there's still a lot of things that need to be considered moving forward with pushing all of these huge amounts of data into the cloud, and how to better protect through access control and data access. Okay, thank you very much. Rajesh, do you have any final comments?
No, thank you, everybody. So the final thoughts are basically, I mean, we know data is valuable and data anxiety is real. And as Peter has explained, basically these data breaches and exploitations are happening, and they are increasing day by day. And the companies, they are not fully ready to protect their data. So these are some of the thoughts from our perspective, how the OS level encryption can provide multiple layers of protections, not just from encryption, access control, device protection perspective, but at least once you combine all these three, then so some of these ransomware attacks and disgruntled employees and all these kind of data exploitation issues can be protected. So, thank you, everybody. So thanks a lot for listening to our talk, and we'll probably now take questions, right, Peter? So after,
yes.
All right. Okay.
Thank you.
All right. Thanks, everybody. Thank you. Bye, guys.